So last week we talked about our product. Today I want to get a bit more technical and talk about some unique system design challenges that Lockbook has faced and how we ended up using Rust to build high-quality cross-platform apps. So as a recap, the two things that I'm going to focus on today is the fact that Lockbook is end-to-end encrypted and that it's cross-platform. There's a bunch of other things that makes Lockbook special, like it's open source and we take notes in open formats. And if you want to learn more about those things, check out episode 1. But the interesting thing about security and privacy is that you can't just offload complexity to your server. This is a common architectural strategy. Maybe it's the default architectural strategy of most companies because it's a machine you completely control. You run any program you want on it. You can control the hardware, as many replicas as you want, and so on. But if you're an end-to-end encrypted app, you can't send that data to the server. You can't have your server solve hard problems like search when your server's not supposed to see them. And so if you're actually doing end-to-end encryption, then your clients end up being a whole lot more sophisticated. And for us, the problem is a little bit worse than that. Any data that we send to our server, if we could pass it through a layer of encryption, even for things like file names, we do that. And from our clients, we don't just expect them to create documents and sort of send them to the server. We expect them to be able to do operations offline, collaborate with people, and perform things like search. And then finally, as if we didn't have enough problems, we didn't really like how JavaScript apps or web apps packaged to be desktop and native apps felt. Even on our high-end machines, they look a little ugly, they're slow to start, they consume a lot of resources. So we wanted to stay away from that. The apps on our devices that felt the best were the native apps that were in that platform's language and frameworks. So on my iPhone, Swift UI apps felt the best to me, or UIKit apps felt the best to me. And on Android, apps written in Kotlin felt the best. And so to take stock of our situation, we're probably going to be writing a number of clients in different programming languages. They're going to be inherently complicated. And if we don't find a way to share code among those clients, we'll probably fail. We probably won't be able to iterate quickly enough and align all the details, especially when you're sending encrypted bytes. When you get details around encrypted bytes or compressed bytes wrong, it's a very frustrating development experience. So if we don't find a way to effectively share code, we won't succeed. Initially, we thought about just running a server on their machine locally. This would allow us to pick any language. We could sort out the details of how to run a server on an iPhone, but I think it was a solvable problem. And maybe that would have worked, but the thing that pushed us away from that is that we wanted a protocol with lower inherent overhead. To just interact with a server, even if it's running locally, you have to sort of serialize a request into some format, context switch to talk to the network stack, send that request, and then your server will do the same things, and then you'll do all the same things on the way back. It's inherently expensive to talk to a different process. So instead, we chose to draw inspiration from SQLite. So SQLite is an embedded database, which means that when your program asks for a query or asks to persist some data, it's inside your process that SQLite's implementation will actually do the underlying syscalls, which will mutate the files. The database is embedded inside your program. And that on its own isn't necessarily special. There's a bunch of embedded database implementations out there. In fact, we wrote our own embedded database, and I'll talk about that in a future video. But what's cool about SQLite is that it's accessible from virtually every programming language that's come out so far. And it's worth studying as a project. How did they pull that off? Obviously, part of that success story is the idea that SQLite is a good implementation, it's stable, it's fast, but I want to reflect on what C as a language gives a project like SQLite. So every programming language that's out there needs to be able to talk to C. Some of our most important libraries are implemented and maintained in C, and if you take your favorite high-level language and you go to definition enough times into a section of code, you're going to find that that concept is either implemented in C or C++, or the compiler expects to link it against some native library or some C library. It's the foundation of our computing experience. So by implementing themselves in C, SQLite got free access to that. C also gave them an obviously inherent performance advantage. SQLite is fast because it's written in C. and it gave them a huge amount of portability. You can compile C anywhere. If you look through the project, its values, you can also tell that C is probably a good culture fit for the creators of SQLite. They probably enjoy writing C, and even if they didn't get those benefits, they probably would have still chosen a language like C. And even if SQLite was much faster and implemented in Java, I don't think it would be as culturally significant as if it was implemented in C. They wouldn't have had access to that language interop. And so, inspired by this, we were looking for a language that would allow us to write fast code, write portable code, and expose a C interface. At the time, I was working at a financial exchange that was writing a lot of Scala code. So I got to see day in and day out, how do they use that type system to save them time? And one of the key ideas was this idea of shift left programming. And so if a defect makes it to your customer and you lose that customer, obviously that's bad. And it would be great for you to catch that defect earlier. It'd be great to catch it at QA time, and it'd be even better if you catch it at test time. And it'd be even better if you could catch it at compile time on the developer's machine. And I sort of saw how they embedded ideas that would have otherwise ended up in documentation or would have otherwise ended up in tests directly into the type system. And I would have thought that it would have slowed down the engineering process, but in that environment, I felt like it sped it up a lot. Usually I would just sit down with my IDE or my text editor, and all the things I would need would be embedded in the type system themselves and in the code base itself. And it was a very productive, flow-inducing environment. And Scala very much was the primary language at the company. Anything that could be built in Scala was built in Scala. But Scala is notoriously slow, so not everything could be built in Scala, and there were some key areas of complexity that needed to end up in C++. And so at this point, the year is 2020, and we start to hear about a language called Rust. And it claims that it has a type system that's as expressive as the one we found in Scala. And it claims that the performance is in C territory. And we had a bunch of questions. We had to figure out if all these claims were legit and would it work for us. So we started to experiment. And the first question was, can we ship a C API using Rust? And we could. And then the next question was, can we build it for the various architectures of Android and the various architectures of iOS? And we found that we could. And then we tried to investigate what is the developer ergonomics of, we're going to have a lot of these endpoints that we'd like to call from Kotlin into Rust and from Swift into Rust and the various other languages that we're using for the prototypes that we're playing around with at this point. And it was a pretty smooth experience. And so excitement started to build on the team, and we eventually just decided to commit and move all of the business logic from these various prototypes that we were working on into a single shared Rust library that we could all start contributing to. This was a really exciting time to be working on Lockbook. The app barely did anything, and so we would go and inside that core library we would implement sort of basic features, basic file operations, and then we'd all split up and implement the various UIs and then sort of regroup and try to understand what's the next thing we could do to make this app feel like an actual note-taking app, something that we could actually use. All of our investments on this front ended up in a library we called Core at that point, but as we learned more about Rust, we realized that that's not a good name for a Rust library, so we renamed it to LBRS, and now this is a published crate and is very much a part of our architectural strategy. From this point on, maybe until 2023, we went on a journey to just make this support all the core operations we cared about and stabilize it. And that itself is a fascinating journey I'll save for a future video, because our journey with cross-platform isn't quite done. There's some more technology we discovered that was game-changing for us. So while we're on this journey to build up LBRS, we're adding more operations to it, stabilizing it, making it faster. It becomes clear to us that LBRS isn't the weakest link. Now, to be clear, LBRS is never going to be done. Even today, I want LBRS to support document history, blame, comments, lower latency collaboration, larger maximum files. I want it to be able to store hundreds of gigabytes of all my data. And it would be very fun to build all of that together. But it wasn't the weakest link. Our core experiences were. So these native UI libraries that we're using, when we're sticking to how they were intended to be used. So all of our iterations of the file tree over the years, showing search results, showing suggested docs, those are all very close to how these UI implementers thought those libraries would be used. But for our more sophisticated experiences, our core experiences, we're using off-the-shelf editors or we're using custom-built experiences, and it's a big drain on resources to even get them up to sort of passable quality. And as we look in the future and we see even larger documents and collaboration and maybe multiple cursors, we know that this is not the strategy that's going to work for these components. To give you an intuition for what's going on, if you start off in some declarative, high-level, very productive framework like Swift UI or React or anything like that, and you go sufficiently down the rabbit hole of trying to make your own experience, you'll leave the world of Swift UI and you'll be in sort of a more procedural world of UIKit. And you go sufficiently far down that route on almost every UI platform, framework, environment, you're going to be in the realm of something like a canvas, where what you're writing is very close to a game. And you're getting a raw stream of events, and you can draw any geometric shapes that you want. You can control your own experience. And we knew we were heading in that direction for things like drawing, for things like our Markdown editor. We wanted that amount of control over the experience. But we didn't want to implement that again in all of these languages. This was going to be a very expensive thing to create. We were willing to create it, but we don't want to create it multiple times. Again, we found ourselves considering JavaScript. This time, with the power of Rust, maybe we can compile to WASM, and we could use a WebKit view or sort of a web view on Android and ship a uniform experience with the power of the web. But again, we sort of wanted to reach for a higher quality solution. We sort of wondered, how did games do it? There's no way games did that. And indeed, they don't do that. Instead of targeting the browser, fundamentally what games target is generally the GPU. So we sort of kept that in the back of our head and researched more. And, could we just target one GPU? We don't want to write multiple GPU implementations. Is OpenGL still a thing, or is that deprecated? And eventually we came across WGPU, which is sort of Rust's GPU abstraction library. And we came across eGUI, which is Rust's immediate mode framework. Immediate mode is exactly what we're looking for when we say, like, we wanted to enter the world of Canvas and get control of the drawing process. So in an immediate mode app, very close to a game, you'll sort of get a raw stream of events. You'll update your state, and then you'll draw your frame. And you have total control over sort of what the geometries end up looking like. Of course, the UI framework has widgets and has sort of ways to help you lay out elements and determine what was clicked and all of those things. But fundamentally, you are in control of that process, and you do have ultimate flexibility. What immediate mode allows you to create is those UI elements that are completely custom, that are completely paradigm breaking. Like, if you think about our Canvas experience, like, how would you express all of these strokes as Swift UI elements? Like, you would never do that. So you have the ability to create things that you would never express in Swift UI. Now, the main trade-off is when you use an app like Swift UI, there's a big depth of things happening for you. If Apple changes the appearance of their whole platform, your app changes automatically. There are ways that your app will magically function on devices that you don't have, so long as you coded it correctly. When an iPad user opens the app, it'll work properly. Or if someone's visually impaired, the accessibility framework on someone's cell phone will help them read your app. With immediate mode, all of those things are possible, but they require specific consideration and investment from you to accomplish. So immediate mode is sort of here, now you can have the tools and you can draw whatever you want, and you need to worry about everything. And for these core experiences, we did want to worry about everything. So we began with eGUI with a small prototype, and it ended up actually replacing our whole Linux GTK4 app. So on Linux, we had experimented with GTK3, we experimented with GTK4, but what we felt as Linux users is, on Linux, what native means is don't use Electron. Don't use some heavy process to build my app. Build it in a language that compiles down to machine code and make it lightweight. and we felt like eGUI was delivering on that promise, and we were way more productive in that environment. So very quickly, our Linux app was an eGUI app, and we built a Markdown editor in there. When that became good enough, then we ran the experiment. Could we do the same thing that we did with LBRS, but now for UI development? Could we take a reference from Metal View, which is sort of a reference to Apple's GPU technology, and could we hand it to WGPU and run an eGUI app within our Swift UI app for just the core experiences? And so we ran that experiment with just the Markdown editor that we were building at that point, and that worked well. We saw, could we expand this to iOS and Android, where the keyboard interactions are much harder to get right, they're much more sophisticated, and that also went well. I expanded on that pattern by bringing over the whole workspace rather than just the editor. So the whole tab strip, the logic for loading and saving documents, and previewing PNGs and PDFs, all of that came over, and we got to delete a huge amount of Swift and Kotlin code out of our platform. And that was a big win for us. Because now we were running workspace everywhere, and the opening and saving code was centralized to one place, we could make it more sophisticated. So we got collaboration out of this. Workspace was also very open source contributor friendly. So anyone who just wanted to sort of make a cool experience with eGUI and LBRS, they could sort of pitch that experience to us, and if it was good, then we could drop it inside Workspace. So what I'm showing here is an open source contributor named Arav made a visualization of what takes up how much space in my Lockbook, letting me figure out what I need to clean up, what's preventing me from syncing, and so on. Another thing I'm showing here is what someone named Krish made. This is a visualization of how my documents link to one another. These are all at various levels of stability, but we could sort of incubate them in their own repo just with LBRS and eGUI, and then as they become more stable, we could integrate them slowly into Workspace and expose more users to them. And so that's very exciting stuff. So now if you wanted to make your own file format for tracking workouts or something like that, Workspace is where you would ship that code, and you could sync the files using LBRS everywhere, and you could show the visual experience that corresponds with sort of your data, and it would be available on all platforms. So we're really excited for what that could turn into one day, and that brings us to today. So now we're all caught up on the cross-platform journey. I hope you found that interesting and informative. All of this is in an effort to make Lockbook more accessible to more people as an open source project. I don't want to just publish the code and hope for the best. I want people to really understand it and be able to interact with it. So once all this background is out of the way, this channel will transition to live coding features that don't exist, sharing my design rationale as it's happening, not just as it happened in the past. So with that being said, I hope you don't hesitate to leave a comment or join our Discord if you have any questions, want to get involved, or there's just a topic you want me to cover in more detail. I'd be happy to do that. Looking forward to seeing you in the next video. Thank you for watching.